Hello and welcome to today's PIR live event webinar brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host. If you're joining us live, please remember that you can ask questions anytime throughout the webinar by clicking on the chat button in the top left corner of your screen and changing the to field so it includes attendees so the others who are with us live can see what questions you are asking. I will relay those questions to our guest when it's time, so you can ask them anytime throughout the webinar. Today's guest is Dr. Nathalie Ouellette. She is the Education and Outreach Officer for the Canadian Particle Astrophysics Research Centre at Queen's University. Thank you so much for joining us, Dr. Ouellette. I'll let you take it away.
Awesome. Thanks for having me. I'm really excited. It's my first webinar working with PIR, so I'm excited to see how it goes. So let me share my slide presentation and we can get going. So is that working well, Stacey?
Yes.
Perfect. All right. So today I'll be talking about the kaleidoscopic universe and all the different ways that astronomers and physicists are learning about the universe. And we use lots of different methods depending on which part of the universe we want to study. So first, we'll talk a little bit about the different kinds of light that exist. So we have something called the electromagnetic spectrum, and that includes all kinds of light. The kind of light that we're most familiar with is visible light because that's the light that is visible to humans. And interestingly enough, that's also the light that the sun emits the most strongly in. And biologists think that that is why humans were designed to see in that range in the visible light. So if our star, the sun, was actually much brighter in, say, the X-ray range of the electromagnetic spectrum, we might actually have X-ray vision. So if you can think of a star out in the Milky Way that is really strong in the X-ray, maybe the aliens that live on planets around that star have X-ray vision, sort of like when you go to the hospital and you go through an X-ray machine. So they would be able to see your bones, essentially. So we have lots of different kinds of light in the electromagnetic spectrum, and the way that we qualify what kind of light it is depends on the size of the wavelength. So all of these light sources basically emit light, and the wave that the light takes can have different lengths. So very, very long wavelengths sometimes can have a wavelength that is several meters or even tens and hundreds of meters long. And those are typically in the radio. Those are the least energetic, longest wavelengths. On the completely different side of the spectrum, you have very, very short wavelengths or very, very energetic wavelengths. And those are gamma rays. And those are the type of wavelengths that if we were to get hit by them, we would have a lot of health issues. Luckily, the atmosphere around the planet Earth protects us from a lot of these different types of wavelengths. So here you can see from the very, very short energetic wavelengths, here gamma rays, all the way down to the long radio wavelengths. And you can see that the atmosphere protects us from the gamma rays, the X-rays, which are the next most energetic, ultraviolet, which you might know a little bit about because when you put on sunscreen, that's what you're protecting yourself from because the sun does emit some ultraviolet light. Then you have a dip in what the atmosphere can block, and you have a big dip in the visible light. And this is good because if the atmosphere was blocking visible light, we would be living in constant darkness. It would be nighttime all the time. If you go to a little bit longer wavelengths, less energetic, you have infrared. And infrared is what we emit a lot in. So maybe you've seen videos taken in infrared light where people look like they're glowing. That's because we emit a lot of infrared. And the atmosphere blocks a little bit of that. So this whole range here, depending on exactly what kind of infrared, you can get blocked. Then you have a big dip again here in the radio wavelengths, and the atmosphere doesn't protect you from radio wavelengths. Luckily, they're not very dangerous, and this is why humans have decided to do a lot of our communications technology around radio waves. So because of all of these different types of light and the different ranges of light that the atmosphere blocks, if we want to study all the different types of light, we need different kinds of eyes in different places. So I mentioned that visible and radio wavelengths aren't blocked by the atmosphere, so we can build telescopes on the planet Earth under the atmosphere to be able to study that light. So you have visible telescopes here on mountaintops, and you have radio telescopes here a lot of the time in the desert, and they can be built on Earth. But if you go into gamma rays, X-rays, UV, or infrared, which are mostly blocked by the atmosphere, you need to build a telescope and send it out into space. So this is why all of these telescopes here have been sent out into space. Now, even in the visible, you can still send a telescope out into space because it's still better conditions, but because it's very expensive, we also have the option to build them on Earth. So why do we want to study all these different types of light? Because maybe we think, oh, we can see in the visible, that's the only thing that's important. But because there's so many different things in the universe, in space, they all emit at different kinds of wavelengths. So if you want to be able to understand the entire universe, you have to study the entire electromagnetic spectrum. So I'll tell you a few examples of different objects that are the brightest in the different parts of the electromagnetic spectrum. So the most energetic part, the gamma rays, which are very short wavelengths, those are really, really big explosions and big energetic phenomena that happen in the universe. So the brightest explosion you can have in the entire universe are called gamma ray bursts. And they're so, so bright that we can basically see them happening at the edge of the universe. But because they're so far away, we don't actually know for sure what creates a gamma ray burst. We just know it's very bright. It might be a special kind of exotic star that collapses on itself. And as we get better gamma ray telescopes, we can hopefully find out exactly what is making this really, really bright explosion. Solar flares are another type of gamma ray emission, and that happens when you have a big explosion on the surface of the sun. So you'll see the solar flare in lots of different lights, but they emit a lot of gamma rays as well. And they can actually disrupt the satellites that are floating in around the Earth a lot. So when you have a solar storm, it can destroy a lot of our technology. But luckily, like I mentioned before, gamma rays are blocked by the Earth's atmosphere. So we're protected by a lot of the solar flare damage that can happen. If you go to the next most energetic, which is X-rays, that's still a lot of things that are exploding in the universe. So here you have the leftovers of a really big star that exploded and went what we call supernova. So some very heavy stars, sometimes 5, 10s, or even 50 times heavier than the sun, will end up exploding at the end of its life. And you'll have a leftover that looks sort of like a bunch of like moss or grass. It's actually a bunch of gas, and it's different colors because there are different elements inside of that supernova remnant. But these emit very strongly in the X-ray. And you also have black holes that emit in the X-ray. So you might be thinking, well, I thought nothing could get out of a black hole, but the black hole has a lot of activity around it. So a lot of the material that's sort of moving around the black hole can end up emitting in the X-ray. And this is one of the only ways we can actually spot black holes because they are invisible. That's why we call them black holes. And if there's light that goes towards the black hole, like visible light, it gets sucked into the black hole, so we can't see it. So if you see a lot of X-ray emission in this particular area and you don't see any visible light, there's a good chance that there's a black hole there. Going to ultraviolet and visible light, you have a lot of galaxies and stars that emit brightly in that part of the electromagnetic spectrum. And the stars emit really brightly in such a way that you can only see the stars. You sort of take out all of the sort of dusty, hazy part of the galaxy when you're looking at the ultraviolet. So on the left here, that's an ultraviolet picture of a galaxy. And on the left, it's a visible light picture of the same galaxy. So you can see, looking at different parts of the electromagnetic spectrum, the galaxy looks a little bit different. And the stars look much brighter in the ultraviolet picture. Moving to infrared light, if you're staying inside a galaxy, the dust part of the galaxy is where you're going to get a lot of your infrared light. And as I mentioned, humans tend to emit strongly in the infrared light. And that's because the strength of the light that you're emitting is correlated or is tied into the temperature of the object that's emitting the light. So we're all about 37 degrees Celsius if we don't have a fever, and that light tends to spike in the infrared. And if you go outside, you'll see that out on planet Earth, a lot of the time in the summer, it's 20 degrees, 30 degrees, so that's still in the infrared part of the light. So you have planets that emit very strongly in the infrared too. So you might recognize this planet here because of its big red spot there that you can sort of see in the infrared around it. But this is Jupiter, and we're using an infrared camera here to look at Jupiter. Now going to the longest types of wavelengths, or the part of the electromagnetic spectrum that has the longest wavelengths, radio waves, you actually have the leftovers of the Big Bang that you can see everywhere in the universe, no matter where you're pointing your telescope. And this is called the cosmic microwave background, because microwaves are a type of radio wave. So your microwave is actually emitting radio waves. And all of this is just sort of like the leftover static noise of when the entire universe was created. You also have big jets that can be emitted from the center of galaxies that have supermassive black holes at the center. So the supermassive black hole at the center is trying to gobble up a lot of food, and it's sort of eating so fast that a lot of the food is sort of escaping from its mouth and is being thrown out of the galaxy in these long jets, and these emit strongly in the radio waves. Now, we talked about the electromagnetic spectrum, and we talked about the different kinds of eyes that you need and the different images that you can get. So this is all one type, the same galaxy. It's a spiral galaxy, and you can see going from the very energetic X-ray to the very low energy radio waves. The galaxy looks quite different depending on what type of light that you're looking at. So at the X-ray, you'll see a lot of hot gas that's sort of in the middle between the stars. In the ultraviolet, you'll have the hot stars. In the optical, you'll have stars that are sort of like the sun, which is why we have the visible light that's visible to us. We were evolved to use that light. And then you'll have cool stars in the dust in the infrared, and then the cold gas. So you can also see that as you have high energy, you have hotter types of objects that are emitting in that light, and then low energy, you have colder elements. Moving outside of the electromagnetic spectrum, we have actually been able to start seeing actual ripples in the fabric of space-time. So sometimes you have really catastrophic collisions that happens. Two black holes or two very, very dense stars like neutron stars will collide with each other, and they will actually create a ripple through space-time. And we've only just in the last 2 or 3 years started being able to observe these gravitational waves that give us a lot of information on how these black holes are created and how they evolve and how they merge together. So on top of all the different types of lights that you can study as an astronomer, you can now also study these gravitational waves. The final way that we can study things in space is by studying the particles that they emit. So all of the different types of objects that I mentioned today emit particles at their core. So the sun emits a lot of particles, black holes, supernovae, and all these particles will travel hundreds and thousands, even millions of light years through space. And when they come into the atmosphere, sometimes they'll sort of create these particle showers. And we have to build special detectors. Often they're built underground in a place called Snow Lab, which is in Sudbury, Ontario. And these big detectors can try to see these particles that come from space to help us understand how all of these objects in space were created and how the laws of physics work. So typically, these particles are very, very small, and they are invisible to the human eye, but we've been able to figure out really clever ways to turn them visible. So this is an example here of a machine called a cloud chamber, and it creates a cloud of alcohol vapor at the center, and every time a particle from space passes through the cloud inside, it creates a track. So this is a way to make all of these invisible particles that come from space visible to you and I. So if you ever come to Kingston, Ontario, near Queen's University, we actually have a cloud chamber here in person that lets you see all these particles. So all the particles have different shapes and sizes, different widths, different, and some curl around, some are very straight. And different types of particles leave different types of tracks. So scientists looking at these cloud chambers can actually tell if it was a really energetic cosmic ray that came from space, or if it was a little electron that left a curly track. So we figured out really nice ways to make all of these invisible things visible to us. So that's basically how we can figure out how to do turn all of these particles visible to us. So astroparticles is another way that we can study the universe. So going back now, I can't seem to find my slide deck anymore. But that's, so essentially, when we want to study the universe, we can use all these electromagnetic wavelengths. We can use gravitational waves, and we can also use astroparticles. So scientists put all of these different pieces together to study the entire universe. So that means if you want to study space, you have all these different options. You don't have to only study one type of thing. So that means there's an entire kaleidoscope of universe and an entire kaleidoscope of jobs that you can have in the future too to study the universe.
A lot of opportunities, it sounds like.
That's
Thank
right.
you so much for sharing that with us. It's very comprehensive on the electromagnetic spectrum today, which is really, really good for context, I think, for those who are watching.
Mm-hmm.
So one of the questions, I guess as the host, I get to put my question first at the top. When I look at images of space, images of galaxies or planets, other phenomena, I always find it interesting that some are real images captured using one of these telescopes, whether it's visible light or a different kind of light, and some of them are artists' renderings. And how do you tell the difference?
So typically, that's a very good question, and it's sort of interesting because people always look at these images and they want to know, if I were to put on a spacesuit and get like binocular eyes and go into space, is this what I would see? And a lot of the time, we have to try and put as much information as possible in these images. So we'll have one color that means X-ray and one color that means infrared, and we'll put them together, and they might be from different telescopes. So you'll always have a little legend at the bottom of these images that will say, in purple, X-ray, in red, infrared, radio waves in blue. So they'll sort of make a little collage of all of these different images from different telescopes and put them together. And sometimes, like for a gamma ray burst, we've never been able to get a really clear picture of it. So we have to hire an artist who will talk to the scientist and try to figure out, okay, what would this look like if we had like an infinitely good telescope that could take a picture of it. So you always have to be very critical and look at the legend and what it says. And then afterwards, if you're interested, you can go and find out more information about how those individual parts of the images were taken.
Very interesting. Well, our next question is from a grade 6 student in asking, when a star dies, what is more likely to happen, a neutron star or a black hole?
So that depends entirely on how much mass there is in the star when it was alive. So you have a certain limit at which point stars will start turning into black holes. And typically, you need a star to be at least 10 times the mass of the sun for it to turn into a black hole. Beyond that point, it's almost 100% chance that your star will turn into a black hole at the end of its life. But below that, typically what you'll end up happening, if the star is about between 4 times the size of the sun and 10 times the size of the sun, it will go supernova, and the leftover at the center of the supernova will either be a white dwarf or a neutron star or something like that. You need to have a massive enough star, like 10 times the mass of the sun, to get a black hole. But if you have that, it's almost 100% sure that you'll get a black hole.
So it still has just a slight variability in there?
Sometimes when the star is at the end of its lifetime, depending on sort of how it expulses or gets rid of some of its mass, it can get a little bit chaotic. And if it loses too much mass and it's just on the limit, it might end up not tipping over into the black hole. But the larger the star is, the more absolute it is that it will turn into a black hole.
Gotcha. And how long does it take for a star to supernova?
So depending on how big the star is, that sort of changes how long the lifetime of the star is. So the sun is about a medium-sized star. And its entire lifetime is about 8 billion years. So it's about halfway through its life. But because it's sort of small, it's actually not going to go supernova. It's going to do something still pretty impressive, but slightly less explosive than a supernova. If you go to larger stars, the lifetime starts shortening down. But once it gets to the point where it's going to go supernova, the actual flash will last on the order of a few seconds to maybe a few hours. And then the light will start going progressively dimmer and dimmer on the supernova. So the actual explosion happens really, really fast, especially compared to the lifetime of these stars, which is on the order of like 100 million years. So it's like a tiny portion of the lifetime of the star.
So the next question I have here is from another grade 6 student at Shaughnessy, wondering how long will it take for a black hole to take up a planet?
So that depends on how close the planet is to the black hole. So we tend to, or in sort of science fiction and everything, black holes are often described sort of like giant space vacuum cleaners. But they're not actually that eager to eat everything around them. So there's something around a black hole called the event horizon. And that's sort of like the black hole's, don't come into my room zone. If you go into the black hole's room, that's when you will never escape. But if you stay very nicely and politely outside of the event horizon of the black hole, you could actually orbit around the black hole for forever, as long as no one pushes you towards the black hole, very, very quietly. So if there was a black hole that had exactly the same mass as the sun at the center of the solar system, it wouldn't actually eat Earth because we wouldn't be inside of the event horizon. We would just keep going around it. Now, if you are inside the event horizon, that becomes a little bit complicated because the gravity inside of a black hole is so intense that it warps time and space. So the gravity of a black hole it essentially makes time drag on slower and slower and slower. So if you were to fall into a black hole, time would slow down so much for you that it would seem like it would take forever for you to fall into the black hole. Time would basically stop for you. So from the point of view of someone from the outside, it would be very fast. From the point of view of the person falling into the black hole, it would literally take forever because that's how weird time works inside a black hole. So we've never sent anyone into a black hole, so we can't know for sure. So this is what our equations tell us. And if we can figure out how to send someone to a black hole and then ask them about it afterwards because they managed to find a way out, maybe we'll find that our theories are wrong.
I love that we calculate as much as we can, but we, at this point, can't know for certain a lot of these things. They're just kind of our best guess.
Yeah.
So that brings me to a more broad question of, is it difficult to become an astronomer? Maybe you could tell us a bit about your career path so far.
Sure. So I grew up in Montreal. And there's a lot of light pollution in Montreal because it's a big city. So I never really had the opportunity to do a lot of amateur astronomy when I was a kid. If I looked outside, I could see the moon, and that was basically it. But my parents were both engineers, and we always talked a lot about science at home. And I knew that I wanted to sort of study something in the natural world or the natural sciences that was like really big, really impressive. Like I wasn't going to be satisfied studying like grass or a tree or something. I wanted something huge. So I thought to myself, what's the biggest thing that I can study? Well, the universe. That's a really big thing. That's basically everything. That's the biggest thing. It's the universe. So I decided that's what I wanted to do. And when I went further into school, into high school, when you have to start deciding the types of classes you want to do, the kind of academic path, I made sure to do all the math and the physics that I could. And I tried to learn a little bit of computer programming on my own because a lot of modern astronomy, you have to like basically stay on the computer all day long and you analyze the data that you get from telescopes, and it's all computer programming. And then I got a physics degree when I went to university, because the university I went to, McGill, didn't have an astronomy program. But every summer, I made sure to do astronomy research working with an astronomer that was at McGill University, because it's really important to have a lot of classes and theoretical work and read a lot of books, but there's no substitute for actually doing research and science. It's very different from taking classes. So listen in class, be very curious, read a lot of books, but make your own experiments too. Participating in things like science fair, or I was part of a robotics club when I was in high school, doing things with your hands, or, you know, programming something, having little projects like that will help you cultivate your curiosity and your problem solving, which is really important. And then afterwards, I went on and I did my grad school, so my master's and my PhD in astronomy, and then I ended up here. So doing a lot of hands-on work is really important, and you have to sort of look for those opportunities yourself. So ask your parents, you know, I really want to get involved in science beyond what I do in class. What are some of the things that we could figure out to do maybe together even?
Wonderful. Now we have some detailed questions that have come in as well, so I want to get back to a few of the nitty-gritty details that we're getting asked about. We have a question here about solar flares, wondering how do they happen, and what is the average time or distance of a solar flare?
So a solar flare will typically happen over a few hours, and typically they sweep the entire solar system. But as you go farther and farther away from the sun, because it's covering a larger and larger area, it becomes weaker and weaker. So if you're Mercury, you get the full blast of the solar flare. If you're Pluto, you'll feel sort of like a gentle breeze on your face, and that's the solar flare. Solar flares are actually, you have little cells on the surface of the sun called convection cells, and the plasma in the atmosphere of the sun sort of, it's like when you're boiling water, you'll have these little sort of circulations of water. You'll have hot water that gets heated up super hot at the bottom near the stovetop, and then it'll go up, and then it'll get sort of cooled off as steam comes off. And so you have these little circulations that happen, and sometimes you build up enough energy that the blast will sort of come back out, and sometimes you'll actually have the solar flare reconnect back down. And it's related to the magnetic field of the sun as well. So it's just energy that sort of explodes off the surface of the sun and then eventually blasts through the entire solar system.
Next up, we have a question about, or a couple questions about our sun. So is it possible for our sun to go supernova? And if our sun turned into a red giant, what would happen to the Earth?
So those are pretty much related, because if we look at how massive the sun is now, or how heavy the sun is now, we know that it's not heavy enough that it will ever go supernova. So we don't have to worry about that. But we do know that stars that have the same size and mass of the sun, typically as they get older, turn into red giants. So we've actually had to think about this scenario, because this is basically what's going to happen in 3 or 4 billion years. The sun will turn into a red giant. So what happens is the envelope of the sun turns redder. It turns a little bit colder, but because it puffs out so much, the sun will actually become, I think, something like 10 times its current size. It will puff up into something really big. So that means the surface of the sun will get a lot closer to Earth. So there are two scenarios depending on how big of a red giant the sun turns. So we know for sure Mercury and Venus are going to be eaten up by the sun, because that's how big the sun is going to get. Now, whether Earth gets eaten up, that we're not sure. So scenario 1, the Earth is eaten by the sun. Scenario 2, it doesn't get eaten, but because the surface of the sun is going to be so much closer to us, it'll get so hot on the surface of the Earth that all of our water will boil off and will eventually just turn into like a barren rock. Luckily, this won't happen for another 4 billion years or so, but by that point, we should probably figure out another planet to live on, because it's not going to be so nice on Earth.
4 billion years. I think that's probably enough time, right?
Probably, yeah.
Now we have a couple questions going beyond our sun that we'll finish off with today. So question now coming from Toronto, wondering if there's more than one solar system. And they're a little bit curious again about black holes. So let's do the solar system one first. Is there more than one solar system?
So technically, because the sun is the only star that we've named the sun, there's only one solar system. It's very special to us, and that's where the sun lives, and that's where we live. But in terms of if there are other stars that have planetary systems around them, there are literally hundreds of billions of them. So in one galaxy, like the Milky Way, you have about 100 billion stars. And we think at least 50% of all stars have at least one planet. And many of them have multiple planets. And we've actually found one other star system that has 8 planets, just like the solar system. So there are tons of other solar systems or stellar systems, stars that have planets around them throughout the universe. And we've only even been able to look at the ones in our Milky Way, but all the other galaxies have them too.
Right. So lots of exploring still to be done.
And lots of potential alien homes.
Right. And so going back to your description of a black hole, so we were talking about how from the outside, a person going into the black hole would seem to happen in an instant, but for that person going into the black hole, it would seem like it was never ending. Mm-hmm. Do we have any best guesses for what would happen to that person going into the black hole?
Yeah, so we are in gravitational fields all the time. We're all in a gravitational field right now, which is why we're not floating out into space. We're all cemented on Earth. And did you know that theoretically, because your head is about 5 feet farther away from the center of the Earth than your feet are attracted to the Earth slightly more strongly than your head. The closer you are to an object, the more attracted you are by it through gravity. But because 5 feet compared to like the entire size of the Earth is so small, it doesn't really make a difference. But when you are in a black hole, the gravitational field changes a lot over the course of 5 feet. So your feet are going to be dragged into the black hole a lot more strongly and a lot quicker than your head. So what ends up happening is that you're actually going to be stretched out because your feet are going to be dragged in faster. And it's called spaghettification. You turn into a spaghetti human, and eventually the bonds that keep your body parts together, all of your body together, will break. So you'll be torn apart before you even fall into the heart of the black hole. So you'll turn into a spaghetti, then you'll be ripped apart. It's a little gruesome, but that's how it is.
So the lesson for today, everyone, is to stay outside of the event horizon of a black hole, lest you become a spaghetti human.
That's right.
So that's pretty much all the time we have today. I would just like to ask one more question. And Dr. Ouellette, what is the most interesting part of astronomy for you, or what's your favorite part?
My favorite part is I love talking to people about science. I love science a lot, and I've loved astronomy for a really long time. So any opportunity I get to talk to people about how much I love science and connect with people like this kind of opportunity is something that I really like. I really enjoy going to the observatory and being able to use these telescopes that, thousands of people have worked on and have cost, hundreds of millions of dollars, and connect with the universe using these like feats of human technology. It feels still very romantic for me when I'm, moving the telescope around and I'm looking up and I'm like, wow, that galaxy is really out there in the universe. And the light that it's sending to me is going either in my eye or like my computer. I feel very special that the galaxy has allowed me to collect its light. So I really still enjoy the sort of classical side of astronomy and connecting with the universe that way.
Well, thank you so much for sharing your passion with us today, as well as some very interesting images and pieces of information about our universe. Thanks so much, Dr. Ouellette.
Thank you for having me.
And next week on PIR Live Event, we're discussing concussions. So more information about this and other PIR educational programming is available at pirweb.org. Have a great day, everybody. Bye now.